Yesterday in our probability lessons, we were looking at one single event, but we were allowing for two different things to happen to be called a success. So the probability of this or this happening, but we were still only drawing one card, or rolling the dice one time. We were only doing one thing, but we were allowing two different things to be called success, so we had that or in there. Today we're going to be looking at the probability of more than one event occurring. So something happening and then another thing happening. Our keyword here is going to be and. That I want the probability of this happening and then this happening. What did we learn is our operation that we use for the word and. Multiplication. So we're going to be multiplying probabilities today. In our problems, we're going to need to consider whether these probabilities are what we call independent or dependent. An independent probability will mean that whatever happens the first time we do something has no effect on the second outcome. So if I flip a coin, I get heads or tails. And then if I flip it again, the coin does not care what it just was. Right? It could just as likely be the same thing it was, or it could be the other thing. Right? So those would be independent events because the coin doesn't care. Okay? In a dependent event, whatever just happened will affect the next outcome. Okay? So in our first example here, it says we're playing a game that involves spinning the money wheel shown. Well, it's not shown on your paper, so we'll get the copy of that up here. Yeah, a lot of probability problems do come from like gambling type examples. I'm not in any way condoning gambling. Actually, by doing these probabilities, I'm hoping to persuade you that gambling is a bad idea. Because as you do the probabilities, you will see the house always wins. So gambling is a bad idea. It's throwing money away, and there are better things you can do with it. If you want to throw it away to your church. Don't throw it away to a casino. So, in this money wheel shown, kind of looks like a Wheel of Fortune type wheel. It says in our probability question, what is the probability of getting more than 500 on your first spin? And the spaces that would meet that criteria are labeled with the A. And then on your second spin, going bankrupt. Okay? And there's two spaces labeled there with B for bankrupt. So we want to know what is the probability that our first spin gives us one of those more than 500 spaces. There are 8 of those out of 24 total spaces on the wheel. I think it's 24 spaces. Yeah. So we're going to multiply by, on our next spin, getting one of those bankrupts, and there are 2 of those.
Okay. Reduce right away.
I would start by reducing. I sat in Mr. Rohr's class the other day as part of my job. I get to sit in on other teachers' classes and observe what they do. And he was talking about multiplying fractions, and he called it producing. So I like that. Instead of multiplying and then reducing your answer, which is going to be very large, reduce them. Start by reducing before you go. So 1/3 times 1/12 is easier to multiply and get 1/36. Okay, the fraction is fine. The decimal is fine as well. So if you want to just throw it into the calculator, 0.028. All right. These are independent events because the wheel doesn't care where it landed on the last time. It could just as easily land on the same space or a different space. Okay. The next example says, a game machine claims that 1 in every 15 people win. What is the probability that you will win twice in a row? Now, when it claims 1 out of every 15 people win, that doesn't mean that like somebody wins, and then there's 14 times that people lose, and then somebody wins, and there's 14 times that people lose. Because otherwise, that wouldn't really be much of a game, right? Everybody would just like stand there and wait for that 15 times, and then like jump on the machine and try to be that person that gets the 15th win, right? So it's random. You could win twice in a row. You could win 3 times in a row. But in the long run, over thousands and thousands of games, about 1 out of every 15 is a winner. Okay? So what's the probability that you're going to win 2 times in a row? Well, the first time you play, you have a 1 out of 15 chance. And because the game is set up randomly, it doesn't care really whether you just won or not. You still have, for the second time you play, a 1 out of 15 chance. So altogether, that is 1 out of 225 which I don't know what that is as a decimal.
0.004444.
Say that again.
0.004 repeating. So you have a 0.4% chance of that happening. So it's not likely, but it could happen. Right.
I'm feeling like
This is like that's like a game.
let's go draw some money.
The next couple questions deal with a customer satisfaction survey. So when
Please pardon the interruption. Middle school students, you can put your books down and get back to class.
the end of March, it's a month thing. So when a company designs a new product, when a company designs a new product or even new packaging, they survey customers to see if they like it. Is this a good product, or are you more likely to buy this now with the new packaging than you would have with the old packaging? And they want to know that they're giving customers what they want so that they can be a successful business. So in a survey, 9 out of 11 men and 4 out of 7 women said that they were satisfied with a particular product. If the next 3 customers they're going to ask are 2 women and then a man, what is the probability that they're all going to be satisfied with this product? So in a previous lesson, we talked about how we could kind of have our blanks. Except we have this problem. 2 women coming through the line and then a man. Using the data we already have, women have a 4 out of 7 chance of being satisfied with a product. The next woman also has independently a 4 out of 7 chance. Her opinion should not be in any way altered by the opinions of the women before her in line. Every person should have their own individual opinion. Then as the man comes through the line, his chance of being satisfied with the product is 9 out of 11. Nothing reduces in this, so we would just need to multiply together all of those tops, 144, and all of the bottoms, 539. That fraction doesn't mean a whole lot to me in terms of likelihood, so this is something that I like to turn into a decimal so that I can get a better feel for it. So I have a little bit better than 1/4 of a chance that the next 3 people are going to say that they like this thing also. Yes.
Why do you have it over W?
I'm just filling my blanks for the people on the line.
Oh.
It's not like a division, it's just lining up my people, 2 women and then a man.
Yeah, that's another fact.
It's a hair product.
How good the product
For example, 4, we're talking about the same data. If 4 men are the next customers, what is the probability that at least one of them is not satisfied with the product? Okay, so we've got some things that could happen here. At least one of them not satisfied means one of them could not be satisfied and the other 3 are. Or 2 and 2, or 3 and 1, or all 4 of them are not satisfied. All those ors mean we have a lot of adding to do. We would have to find each of those and then add them up. We could do it that way, but that seems like a lot of work. Okay? So the other way of doing this problem is thinking about what is the opposite scenario. So what is the opposite of, what is the only case that is not covered by at least one not satisfied?
All of them.
All of them are satisfied. That's the opposite of this. At least one not satisfied means 1's not satisfied, 2's not satisfied, 3, or 4. Okay? The only other option is 0 are not satisfied, which means all are satisfied. And we learned yesterday that when we talk about this opposite probability, we can do 1 minus. So we're going to do 1 minus the probability of all satisfied. The probability that all 4 of them are going to be satisfied, well, each of them are men, and each of them individually has a 9 out of 11 chance of being satisfied with this product. So we would throw this in the calculator and find 0.552. So it is more likely than not that at least one of these guys are going to say they don't like it. Okay. You have a problem like this in your assignment about basketball free throws and like making or missing them, and it will be easier in that one to think about the opposite scenario. Okay.
Oh, that's easier. We'll just collect
Questions?
Oh, and you like you weren't even playing last week. That was the coach's swap.
We can do probabilities from data as well. So it says the table shows, and I'll show it to you in a second, the number of endangered and threatened animal species in the United States as of November 30, 1998. So we have a chart with some data.
19 what?
That's when our book was published, so that's why all the data comes from 98. So in this chart, it gives us how many animals from kind of each animal class are either endangered or threatened. Okay. Our question asks us, in part A, find the probability that an animal listed here is a reptile. So what would I do for the probability of a reptile? 14 plus 21, so all of the reptiles, 35, divided by all of the animals, the entire chart added together. And the entire chart has 475 animals listed on it. So we could either reduce that fraction or just divide it out and get 0.07. So 7% chance that a reptile is endangered or threatened. Okay, 7% of the endangered or threatened animals are reptiles. Part B says, what is the probability that an endangered animal is a reptile? Probability that an endangered animal is a reptile. Well, if we're talking about endangered animals, we don't care at all about these, right? The probability an endangered animal is a reptile. We don't care at all about threatened, so we're going to completely ignore that data. So then what would I do?
14 out of the rest.
14 out of whatever the rest of that top adds up to. Only the endangered, because we don't care about the threatened in this problem. We're specifically talking about endangered animals. So I don't actually know what that is. I didn't write that down.
355.
What is it?
355.
355? So then we get 0.039. So about a 4% chance that under the endangered category, it's a reptile. Okay? Questions? This is what we call a conditional probability, where we're breaking it down to just having one condition that we're looking at. We're just looking at the condition of endangered. Okay? I have a couple of examples of card problems. You will have some like this in your homework and some like this on the test. So these are kind of big deal questions. Remember, if you're not comfortable with a deck of cards and what comes in a deck of cards, you do have that page in your packet that shows you. And when it comes to the test, if you're still not comfortable, I'll give you a copy of that page so that you'll have that to reference. So in these problems, we're going to be doing the same thing 2 different ways. In each question, we're going to be drawing 2 cards. So the first one says, what is the probability that the first card is not a face card and the second card is a face card if, and then our part A is if we replace the card, okay? So I draw a card, I look at what it is, I put it back in, shuffle up, draw a new card, and look at what it is, okay? So, how many not face cards are there in the deck of 52? 40. So there's 12 face cards, so there's 40 not face cards. And, okay, and then I shuffle it up and put it back in the deck. How many face cards are there now? 12 out of 52. Okay, I'm going to bring this to a decimal. 0.178. Now part B, I want the same thing to happen. I want to draw a not face card and then draw a face card, but it says you do not replace the first card. So I'm going to draw that card, I'm going to keep on holding on to it, and draw another card. We assume success on the first draw. Okay? So on my first draw, how many not face cards are there in the deck? 40 out of 52 cards in the deck. Now we assume I did that successfully, that I managed to draw a card that is not a face card. So in my hand, I'm holding a card that is not a face card. Now I'm going to draw again. So how many face cards are left? 12 out of how many cards are left? 51.
So
Because I'm holding on to one.
Oh.
Always assume success on your first draw. So we multiply that out, and I get 0.181. I always go to decimals on these kind of problems so I can compare my answers. They should be just slightly different. If they are very different, you've done something wrong. Okay? We're only taking one card out of the deck, so it's going to make a difference, but it's not going to make a huge difference. Okay? So your answers should be close, but not perfect.
And what was the difference between the first problem and the second problem?
In the first problem, I put the card back in before I drew the second card.
Okay.
In the second one, I kept holding on to my first card. One more of that type of question. You randomly select 2 cards from the 52 card deck. What is the probability the first card is a diamond and the second card is red? And in part A, we replace. So diamond, how many diamonds are there? 13. Then I assume I did that. I put it back in, shuffle it up, draw another card. Now I want to draw a red card. How many red cards are there? 26 out of 52 because I put the card back. Throw that in the calculator, 0.125. Part B, I'm going to draw, hold on to my card, and draw again. So the first is still the same because I haven't done anything yet. So there's still 13 diamonds out of 52 cards. But now I assume I successfully drew a diamond. So I assume I am holding on to a diamond. How many red cards are left in the deck? 25, because a diamond is red and I'm holding on to one of them. Out of how many cards are left in the deck? 51. I throw that in the calculator, and I get 0.123. Again, very close to the same, but they will be slightly different. The first problem where we're replacing the card is an independent probability problem. The deck doesn't care what you drew the last time if you're still drawing from the whole deck. In the second one, where we're not replacing, that is a dependent probability because taking that card away changes our chances for the second outcome. Okay? So in these, we're looking at an independent situation and then a dependent situation. If we don't replace the card, then what we've already done affects our next term. Okay? Questions on those? You and 2 friends go to a restaurant, order a sandwich. There's 10 sandwiches on the menu, and none of you are picky eaters, so you could each order anything. What is the probability that each of you orders a different type? Okay, the first person that orders, they're kind of lucky. They get to choose anything, right? So that person could have 10 out of 10 sandwiches. The next person, if our goal is to get different sandwiches, has what? 9 out of 10 sandwiches they could choose. And the third person, 8 out of 10 sandwiches they could choose. Throw that in the calculator, 72% chance you're all going to get something different. Okay. One more type of problem to look at. We have 2 examples of this type of problem where we're going to use what's called a tree diagram. The American Diabetes Association estimates that 5.9% of Americans have diabetes. Suppose a medical lab developed a simple diagnostic test that is 98% accurate for people who have the disease and 5% accurate for people who do not have the disease. Okay, so what that means is you go to a doctor, they test you for diabetes. If you actually have diabetes, this test will tell you that you have it 98% of the time, but 2% of the time it's going to tell you that you don't, even though you really do. Okay? If you don't have the disease and you go in and you get tested, 95% of the time it's going to tell you that you don't, but 5% of the time it's going to give you what we call a false positive. It's going to tell you that you do have it. This is why they do medical tests more than once. They don't want to start treating somebody for something until they're really sure that they have it, and no medical test is 100% accurate. Okay? So what we're going to do in these problems is break down our population. So the first break in the population that we're going to give is people either have diabetes or they don't. There's not like a gray area on that, right? You have it or you don't. You can't kind of have it, right? So we're going to break down our population. So this tells us that 5.9% have it, or 0.059. So then how would we figure out about who doesn't have it?
Subtract that from 1.
Subtract that from 1, because this should cover everybody, right? You either have it or you don't. Now we're going to break down these groups further and say that they either get an accurate test or not. If you have diabetes, it says the test is 98% accurate, which would mean it is 2% inaccurate. If you do not have it, it is 95% accurate, which means it is 5% inaccurate. You can maybe see now why these are called tree diagrams. They start to branch out and kind of look like tree branches as we build our categories here. Okay. Always work with the decimals, not the percents. Okay, always change the percents in the problem into decimals. Now our question asks us, if the medical lab gives the test to a randomly selected person, so this could be a person who actually has it or who doesn't, what is the probability that they get a correct diagnosis? Okay? There are two different ways this could happen. They could either have diabetes and get an accurate test that says they do, or they could not have it and get an accurate test that says they don't. Okay, I'm going to say that again, and I'm going to emphasize the key probability words. They could have diabetes and get an accurate test, or they could not have it and get an accurate test. Okay, so they could have it and get an accurate test. What does and mean? Multiply. So we're going to do 0.059 times 0.98, and we multiply. So they could have it and get an accurate test. Or, what does or mean? Add, they could not have it and get an accurate test. So we're going to multiply those. We throw all that in the calculator, and it gives us 0.952, or 95.2%. So this test is in general for the population 95.2% accurate. To be able to check the validity of your answer should always be the closest to that for the majority of the population. So the majority of the population does not have it. It should be the closest to their percent of 95%. It'll be a little bit skewed by the other one, okay, but it's going to be the closest to where the majority of the population lies. So you should make sure that your answer is pretty close to that. If it's not close to that, you probably did something wrong. Questions? Let's try one more tree diagram. In one town, 95% of the high school students graduate. So that's our first break in the population. Is people are either graduating or not graduating.
How big is the town?
Hypothetical. It says 95% are graduating. So that's going to be 0.95. And 5% don't. Suppose a study showed that at age 25, 81% of the high school graduates had a full-time job. So if they graduate, then we're concerned about whether or not they get a full-time job. 81% do, which means 19% don't. And if they don't graduate, then it says 63% get a full-time job, which would mean 37% don't. So what is the probability that a randomly selected person is going to have a full-time job? So they could either graduate and then get that job, or not graduate and get that job. So our ands, we multiply along our branches, or we add up those branches. Now before we actually calculate this, what should our answer be close to? 81%. So the majority graduate, so we should be close to their value of 81%. Is it going to be bigger or smaller than 81%?
Smaller.
Smaller because the other group is lower, so it's going to pull it down. It's just not going to pull it down a lot. Okay? So we type it in the calculator, and I get 0.801. Okay? So it pulled it down a little bit less than a percent. Not a big change, but just a little bit. Okay? All right, for your homework, the first group of questions refers to spinning a colored wheel. Your copy of your homework assignment is in black and white, so that causes a little bit of a problem. So you will need to have these values. On this colored wheel, there are 3 red spaces. There are 4 blue spaces. There are 4 green spaces. And there are 5 yellow spaces.
Numbers are those?
So that is for numbers 12 through 17. You will need to have those values. It doesn't matter where they are on the wheel, okay? So you don't really need to assign them to particular places on the wheel. You just need to know how many of them there are on the wheel. Okay? So those are all the colors that show up on the wheel and how many times each of them show up.